Welcome everyone. So in this session, we are going to see how to design modern counters. We'll see how to design modern counters using various flip-flops, JK, SRT and D flip-flops. Now before we go to the designing of modern counters, let us summarize the truth table and excitation table for various flip-flops. Now the first flip-flop what we have seen is an SR flip-flop. The truth table for an SR flip-flop, we have the inputs S and R and output is Q. For the combination 0, 0, Q was equal to Q. For the combination 0, 1, output was equal to Q was equal to 0. For the combination 1, 0, Q was equal to 1. And for the combination 1 and 1, Q was equal to a forbidden state. For 1 and 1, we had a forbidden state combi. Now this was the truth table for SR flip-flop. Now if you see the excitation table for SR flip-flop, the excitation table for SR flip-flop was, we had the inputs Qn and Qn plus 1. So Qn and Qn plus 1, I will write it as, okay, Qn and Qn plus 1. So the combination was Q was 0, 0, Qn plus 0, 0. Next combination it was 0, 1. And next it was, we have 1, 0. And the last combination will be 1 and 1. Then we have the inputs Q and Qn excitation table for S and R. That means if you want to design any circuit for which S and R is the input, in that case we can use this. So for 0, 0 combination, what was the excitation table? Excitation table was X and 0. For 0, 1, it was 0, 1. For 0, 1, we are having 0, 1. For 1, 0, it is 1, 0. And for 1, 1, the excitation table is, for 1, 1, the excitation table is 0 and X. So this is the excitation table for SR flip-flop. We should always remember the truth table and excitation table for designing any sequential circuit. Next, we have the truth table and excitation table for JK flip-flop. So JK flip-flop, J, K, Q is the input. J is 0, K is 0, Q will be equal to 0. Truth table, Q will be equal to Q. J is 0, K is 1, Q is equal to 0. J is 1, K is 0, Q is equal to 1. J is 1, K is 1, Q will be equal to Q bar. Toggle state. So this is the truth table for JK flip-flop. Now what about the excitation table for JK flip-flop? Again, excitation table will have the inputs Q and Qn. I have the inputs Q, Qn and Qn plus 1. So I will write it as Q and Q plus 1. It is Qn and Qn plus 1. And this will be J and K. If Q and Qn plus 1 is 0, 0, what will be J and K equal to? J will be equal to 0 and K will be equal to X. If Q is 0 and Qn plus 1, Qn is 0 and Qn plus 1 is equal to 1, this JK value will be equal to 1 and X. Next combination will be 1, 0. If it is 1, 0, this will be equal to X and 1. The last combination is 1 and 1. If the value is 1 and 1, this will be equal to X and 0. So I have a X and 0. This is the excitation table for JK flip-flop. Next we have the T flip-flop, D flip-flop and T flip-flop. For D flip-flop, what is the truth table? If D is 0, Q is 0. If D is 1, Q is 1. I have only one input and one output. Q is always the output. In the truth table, Q is the output. In the excitation table, Q and Qn are the inputs, SR will be the output. So this is the truth table for D flip-flop. Now if you write the excitation table for D flip-flop, it will be Qn and Qn plus 1. I can also denote this by, I denoted it using Q and Q plus 1. Both means it is Qn and Qn plus 1 what I'm talking about. So this is 4 combination I'll be having 0, 0, 0, 1. I have 1 and 0, and next one will be 1 and 1. This is D. If Q and Qn plus 1 is Q and Qn plus 1 is 0, 0, D will always follow this Qn plus 1. So we can write directly D is following Qn plus 1. So it is 0, 1. Now what is the truth table for D flip-flop? Now the truth table for D flip-flop is D, we have the inputs D and output will be Q. If D is the input, output will be the same. Again, if D is equal to 1, output will be equal to 1. So if D is equal to 1, output will be equal to 1. So D is equal to 1, output is equal to 1. Now what about the excitation table for D flip-flop? I'll be having the inputs Qn and Qn plus 1. And I'll be having the output as D. The combination will be 0, 0. So if it is 0, 0, D will follow Qn plus 1. So in first combination is 0, 0. Next combination is 0, 1. So this D will be equal to 1. And next combination is 1, 0. Next combination is 1, 0. So D will be equal to 0. And the next combination is D is equal to 0. Next combination is 1 and 1. So D will be equal to 1. Clearly we can see that D is following your Qn plus 1. Next what we will do, we'll write the excitation table for T flip-flop. So if I write the truth table for T flip-flop, so if I write the truth table, first I'm writing the truth table T and Q. If T is equal to 0, Q will be equal to Q only. If T is equal to 1, Q will be equal to Q bar. This is the truth table for T flip-flop. Now if I write the excitation table for T flip-flop, it will be Qn, Qn plus 1. And next it will be equal to T. Now what is your Qn? Qn will be 0, 0. If it is 0, 0, 4 combinations, let me write 0, 0, 0, 1. And this is equal to 1, 0. And this is 1 and 1. If Q and Qn plus 1 is 0, 0, what will happen? T will be equal. Now this is the excitation table for T flip-flop. You can see that the excitation table for T flip-flop follows the XOR gate. So this is D flip-flop table, truth table. This is excitation table for D flip-flop, truth table for T flip-flop, truth table for excitation table for T flip-flop. And previously we had the truth table for SR flip-flop, excitation table for SR flip-flop, truth table for JK flip-flop, and excitation table for SR flip-flop. Now what is that we want to do? Our aim is to design a modern counter. Okay. Now we are going to design a modern counter. You can design a modern counter using any flip-flop. Currently we are going to design a mod 6 counter using JK flip-flop. You can design it using T, D, SR and T, D, SR. We are doing now with JK flip-flop. Okay. Mod 6 counter. Now what do you mean by mod 6? Mod 6 counter means the counter will count from 0, 0 to 1, 0, 1. That means it will count from 0 to 5. If you have to implement a mod 6 counter, the minimum number of bits required to implement a mod 6 counter will be 3 bits. 6 to represent 6, we need 3 bits. So the minimum number of bits required to represent a mod 6 counter will be only 3 bits. So mod 6 counter will always count from 001 to 101. That is, it will not go to 6, it will stop at 5. Now if it stops at 5, totally we will be having 6 states. So it is stopping at 5, we will be having 6 states. Now let us design a mod 6 counter using JK flip-flop. Now when you're designing a counter using any flip-flop, we should consider the excitation table for that flip-flop and we should use that to design. So mod 6 using JK flip-flop. Excitation table I told. Mod 6 counter requires 6 states. So 3 bit, we require minimum 3 bits, which indicates that we require 3 JK flip-flops. So we require 3 JK flip-flops. QA, this is the output from first flip-flop. QB is from second flip-flop. QC is from third flip-flop. Next, QA plus 1 is the output of the first flip-flop. QB plus 1 is the output of the next flip-flop. QC plus 1 is the output of the third flip-flop. And what did I tell you? We need 3 JK flip-flops. So the inputs will be JK, JB, KB, JC, KC. So we'll be having JK, which represents first flip-flop, JB, KB, which represents the second flip-flop, JC, KC, which represents the third flip-flop. Now come to the combinations, input combinations. Now since I have QA, QB, QC, what are my combinations for QA? This combination will be, it will start from 0, 0. Inputs will be 0, 0, 0 to 1, 1. No change in that. But we should see the output. After 0, 0, 0, what will be the next state? Next state will be 0, 0, 1. There is no change in that. Now after the 0, 0, the next input combination will be 0, 0, 1. So what will be the output? If your present state is 0, 0, 1, next state will be 0, 1, 0. Next, if the present state is 0, 1, 0, what will be the next state? Next state will be 0, 1, 1. So next state will be 0, 1, 1. What is the next combination? If the present state is 0, 1, 1, what will be the next state? Next state will be, have I written the truth table? This is, this should be 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1. Correct. So if the present state is 0, 1, 1, the next state will be 1, 0, 0. Now if the present state is 1, 0, 0, next state will be 1, 0, 1. Now if the present state is 1, 0, 1, what will be the next state? 1, 0, 1. Present state is 1, 0, 1. What will be the next state? The counter will count only from 0 to 5. 5 is ending over here only in the previous state. So once it comes to sticks, it should go back to 0. So the next state will be 0, 0 and 0 only. Okay. Then after 1, 0, 0, 1, 1, 0, 1, we have the next combinations in the truth table. 1, 1, 0. When it goes to 1, 1, 0, this we don't require at all because it is going back to 0. So this will be a don't care state. Again, when I take 1, 1 and 1, again I don't require a state. This will go back to a don't care state. Okay. So now let me write the K map. Write the J and K values. Now to write J and K values, if I have to write JA and KA, I should follow QA and QA plus 1 and use the excitation table. I should follow QA and QA plus 1 and use the excitation table and write JA and KA. Now if you can see, what is QA over here? QA is 0, QA plus 1 is 0. For 0 and 0, according to the excitation table, it will be 0 and X. Similarly, follow this and write the excitation table over here. So next is also 0 and 0. So this will again be 0 and X. Next combination, third one is also 0 and 0. So again it will be 0 and X. Now the fourth combination will be what is the fourth combination? Now the fourth combination according to the truth table is 0 and 1. Since it is 0 and 1, what is the excitation table? If Qn is 0 and Qn plus 1 is equal to 1, according to the excitation table, the value will be J and K value will be 1 and X. Next I have 1 and 1. If I have 1 and 1, what is the excitation table value for my JK? It will be, for 1 and 1, it will be X and 0. So the next value will be X and 0. Next combination is, the next combination if you can see, it is 1 over here and 0. So when it is 1 and 0, what is my truth table value, excitation value? It will be X and 1. 1 and 0 will be equal to X and 1. And the last two combination, you can see 1 and X, 1 and X. Since an X is there, we don't know what will be the state. So this will be X and X, and even the next state will be, next state will also be X and X. Now this is for JA and KA. How did I write JA and KA? I saw QA and QA plus 1 and I wrote JA and KA. Now I should write JB and KB. To write JB and KB, I should follow QB. I should follow QB and QB plus 1 and write JB and KB. If I follow QB, what is the first value? It is 0. And what is QB plus 1? QB plus 1 is also 0. Since both is 0 and 0, if I write this value, JB, KB will be equal to 0 and X. And next value, this value will be 0 and X. So I have this as 1 and X. And next value will be X and 0. So I have this as X and 0. And the next value for 1 and X will be X and 1. X and 1, 1 and 0 is the next combination. So I will be having X and 1. Follow QB and QB plus 1 and complete the truth table for JB and KB. Follow QC and QC plus 1 and complete the table for JC and KC. Now once this truth table is completed, what is our next step? Next step is to write the K map. So I have to write the K map for this truth table and solve the K map for JA, KA, JB, KB, JC and KC. Now this is a complete excitation table for mod 6 counter using JK flip-flop. I've written the J, KA, JB, KB, JC and KC values completely. Now let me solve this. We have to solve for KA. First, what we have to do is, the inputs will be QA, QB, QC. We have to solve for JA and write the K map. Again, inputs will be QA, QB, QC. We have to solve for KA and write the inputs. Next, JB and write the K map, KB and write the K map, JC K map, KC K map, and write down the expressions. So first, what we will do, since I know QA, QB, QC, first K map I'll write for J map. So now I'll solve for K map. I'll write K maps for JA and KA. So first I will write the K map for J. Now what are the inputs? My inputs will be QA, QB and QC. So this is my K map. Three variable K map, QA, QB, QC. I'm writing the K map for JA. So here I'll be having 0 and this is 1. Here I'll be having 0, 0. Next it is 0, 1. And here it is 1 and 1. And next it is 1 and 0. Now see the K map. When your input is 0, 0, 0, what is your JA value? J is 0. 0, 0, 0, J is 0. 0, 0, 1, J is 0. 0, 1, 0 is 0. And next I have a 1. This I am writing from K map, this K map. And the remaining all values are X, X, X and X. Now, how is this K map? Here I have QA and on this side I'll be having, it is QB and QC. Okay. Now, how can we solve the K map? First, we have to check whether we are having an octet. Do we have an octet over here? We don't have an octet. So next, we have to check whether we are having a quad. Do we have a quad over here? We don't have a quad. So next thing what I have is a pair. I have one pair over here. Now, if I solve for this pair, what will be the expression? So 0 and 1 we cannot consider. This will be left out. 1 and 1 represents QB and QC. So the expression will be JA is equal to QB into QC. Done. Next, similarly, we have to write the K map to solve. Next K map, similarly, we have to write the K map to solve for KA. Now we'll write the K map for KA. So this will be the K map for KA. Now what is happening in KA, if you can see, it is 0x . So the first value is an x. For 0, 0, 0, I get an x for KA. So this will be an x. For 0, 0, 1 also it is an x. This is also an x. This is also an x. Next I will be having 0, 0. Then I have 1. Then the other two values is x and x. Now I have to simplify. Now this one, again, you can either group it this way or you can group it this way. It is your choice. So even in the previous J also, you could have grouped it accordingly. So I'll group it this way. Now what will be my expression for KA? Now the expression for KA will be equal to QC. I've grouped it. Now how did I get this? I've taken QA, QB, QC as inputs and I've written the K map for JA and got the first expression. I've taken QA, QB, QC as input and I've written for KA, second expression I've got. Similarly, you have to take QA, QB, QC and solve for JB. Write the K map for JB. JB I will get is QA bar into QC if you solve it. Again, you have to write for KB. KB will be equal to QC. I'll get another expression for KB. Now, again, you have to write the expression for JC and KC. So, I'll just show the expression for JC and KC. One I'll show. Because this is an exclusive variant of K-map, so I'm showing this. Now, if you can see for JC, let us write down the values for JC. It is 1, don't care, 1, don't care, 1, and all others are don't care. So, if I write all others don't care. Now, how will you simplify this? If you simplify this, you can see that there is an octet over here. So 1 don't care, 1 don't care. If you can group it, you can group it together. This will form a complete 8 ones I have, octet. It is a rectangle. Rectangle ones are there, so this is an octet. So what happens now, if I write the expression for JC, JC will be equal to 1. JC will be equal to 1. Similarly, if you write the expression for KC, KC will also be equal to 1. Now we have got the expression for JA, KA, JB, KB, JC and KC from the truth table and the expression. Now what we have to do, we have to design the circuitry. So to design the circuitry, how many flip-flops we need? We need 3 flip-flops, 3 JK flip-flops, because as the question is, design a mod 6 counter using JK flip-flop, or you can design it using any flip-flop, but it is mentioned we have to use JK flip-flop. Now to count from 0 to 5, mod 6 will count from 0 to 5, we require 3 bits. So it is a 3-bit counter. 1 bit is represented using 1 flip-flop. For 3 bits, we require 3 flip-flops. So I take 3 JK flip-flops over here now. JK, JK and 3 JK. Done. Now clock. Actually clock should be given using this clock pulse. But I want to visualize the output, so I'll give clock using this. But actually clock is a sequential element like the pulse. So as of now, we are going to give clock from this one to visualize the output. All flip-flops are clocked simultaneously. Since it's a synchronous circuit, so I can give the same clock. Synchronous mod 6 counter is what we are designing. Done. Now I have JA over here. You can see this is J and this is K. So let me label this as clock. Okay, this let me label it as flip-flop A, FFA. And this I'll label it as flip-flop B. And this I will label it as flip-flop C. This I don't want this. This is representing this part. You can assume this one. Okay. Now, in this flip-flop, I have J and K. This is A flip-flop. So what is the input for this flip-flop? Input for this flip-flop is JA. JA and KA. Now what is JA and JA is equal to QA into QC. So I require an AND gate. Okay. Now what is the input to the AND gate? Before that, let me label the output so as it is easy for us. So what is this output? This is nothing but QA. If this is QA, this one should be QA bar. So the first output what I've labeled is QA. This is QA for us. QA. Next, let me label QB. I have a QB. This is QB for us. So let me label this as QB. What is this? This is QA. And I have another output. This one, let me label this as QC. This is nothing but QC. Now we'll see what is JA equal to. JA is equal to QB into QC. So QB is over here. JA is equal to QB. I'll connect it to QB. JA is equal to QB into QC. So I'll connect it to QC. Where is my QC? This is my QC. Done. This goes to what is this? This is going to the input to JA. Okay. Now what is the next one? KA is equal to QC. So I have KA over here. This I should connect to QC because this is going to QC. Next, what is JB equal to? JB is equal to QA bar into QC. So again, I need an AND gate. Take an AND gate. So JB is equal to QA bar. I think this is Q. If this is QA, the other input will be QA bar. I can take from here, or I can give a NOT gate to QA and I can connect. So JB is equal to QB bar into QC. So this is my QC. QB bar into QC. What is this? This goes as input to JB. So this is not a JB. The flip-flop was not a JK flip-flop. So this is JK and this is JK. So this is QC. This is clock to both the flip-flops. This is QB. Okay. So now what is the thing we are discussing? We had to give the input J. So this is JB is equal to QA bar. This is A flip-flop. So this is QA bar. And this is QC. Perfect. So this should go to J. Gone. Now what is, JB. Now what is KB equal to QC? KB is equal to QC. So here it is KB connected to QC. This is QC as we know. And what about JC and KC? JC and KC is equal to 1. So I'll give a logic 1 over here. This is logic 1 connected to so JC, I can give a JC over here and connect it to JA and JC and KC. So JC is connected to logic 1, KC is connected to logic 1. Done. Now let us analyze whether it is working. That's all. This is the design. So first you have to take QA, QB, QC. Check how many bits are required. Each bit represents one flip-flop. This is a mod 6 counter. Now suppose if you have to design a mod 10 counter. Mod 10 means it has to count from 0 to 9. To represent 9, the number of bits required is 4 bits. So we require 4 flip-flops. Here we require only 3 flip-flops. So this is done. And write QB, this one, next state. First you have to write the present state. Then the next state, write down the flip-flop values from the excitation table. Write K-map, solve for JA, KA, JB, KB, JC, KC. Use this and draw the diagram. So during the first clock cycle, 0, 0, 1. Next, 0, 1, 0. Next, 0, 1, 1. Next, 1, 0, 0. Next, 1, 0, 1. What should be the next state? Next state should be 0, 0, 0 because our flip-flop will count only from Our counter is counting only from 0, 0, 0 to 5. So the next state should be 0. So 0. Then again it will go to 1, 2, 3, 4, 5 and 0. So our design is perfect. So let me summarize the steps. Steps. What are the first step? First step is identify the number of bits. Bits required. Second step, number of FF is equal to, second step is number of flip-flops is equal to number of bits. Then third one, write the truth table. Write truth table from excitation table. So write truth table from excitation table. I will tell, write present state, next state and flip-flop input. Flip-flop input is written from excitation table. So I will write it as EP. Fourth step is solve using K-map the FF inputs. Then draw the logic diagram. Fifth step will be draw the diagram. So that's all is regarding your design of mod 6 counter using JK flip-flop. Thank you.
Now we'll see design of mod 6 counter using D flip-flop. QA, QB, QC are the inputs. QA plus 1, QB plus 1, QC plus 1, DA, DB and DC. The mod 6 counter will count from 0 to 5. So 0, 0, 0. Next state will be 1. If your next state is 1, it is 2, 2, 3, 3, 4, 4, 5. See, when your present state is 5, it goes to 0. Now, according to the transition table, DA will follow the next state. So whatever is QA plus 1 will be equal to DA. Whatever will be QB plus 1 will be equal to DB. Whatever is QC plus 1 is equal to DC. This can also be written from the excitation table. This is a transition table. You can also write this from the excitation table for D flip-flop. Now, keeping these things, let us plot DA. Now, when you're plotting the DA, we require a 3-variable K-map. So I have a 3-variable K-map, QA, QB, QC, 0, 0, 0, 1, 1, 0, and 1, 1. Next, 0 and 1. What are the values for DA? It is 0, 0, 0, and 1. And next, it is 1, 0, X and X. Now, if you simplify the K-map, let me simplify, get a pair over here. Now, keeping this pair, if I write the expression, there is one more pair. So, 2 pairs are there. What will be the expression for DA? DA will be equal to QA into QC plus QB into QC. Similarly, if you write for DB, we'll get the expression for DB. And then if you write for DC, we'll also get the expression for DC. Let us write for DB. And this is the truth table K-map for DB. DB is equal to 0, 1, 1, 0, 0, 0, XX. There is one pair over here and there is a single. This pair results in QB in QC bar and the single is QA bar into QB bar into QC. Similarly, we can also write the K-map for DC. DC will be equal to, so this is a pair. I have one, I'll get an quad over here. If you can see, I'll get a quad. Now, if I simplify this quad, I'll get DC is equal to QC bar. Since mod 6 is a 3-bit counter, which will count from 0 to 5, I require 3 D flip-flops. This is designing using D flip-flop. DA, DB, DC. Let us connect the clock. Again, you have to use a clock like this. Since we'll not be able to visualize the output, I've used a gated clock. Then what is DA, what is DB, and what is DC we have to connect. Now DA is equal to QA into QC bar. So I require 2 AND gates and also 1 OR gate. And this is DA. What is DA? QA. So let me take QA. You should make the connection such that shorts are avoided. QA into QC bar. So here it is QC bar. QA into QC bar plus QB into QC. So this is QB. QB into QC. Then DB is equal to QA bar into QB into QC. So I require a 3 input AND gate. So let me keep a 3 input AND gate. QA bar into QB bar into QC. And one more AND gate. And one OR gate. So this is nothing but DB. What is the inputs to DB? QA bar. So I already have QA. I can also put a NOT gate and make it as QA bar. This is QA. This is QA bar. Then QB bar. You can either tag the signal from QB or make it as a bar. Both will work. So QA bar, QB bar, and the next one is QC. QA bar into QB bar into QC. And the next, for the other one, it is QB into QC bar. So where do I have my QB? QB is over here. QB into QC bar. So now this is all regarding the connections for mod 6 counter using D flip-flop. It is simple. Just formulate the equations, obtain the Boolean expressions from the K-map and do the logical connections. Let me check whether it is working. Welcome everyone. In this session, we will be seeing design of mod 6 counter. So I'll be taking the same example, mod 6, whatever we have done earlier, mod 6 counter using T flip-flop. Mod 6 using T flip-flop. Now, whenever we are designing a mod n counter, first we have to have the excitation table with us for reference. or we can keep it with us. So I'll write the excitation table. I'll rewrite the excitation table for T flip-flop. So what are the inputs? My inputs will be Qn and Qn plus 1, for which my output is nothing but T flip-flop because I need a T flip-flop. 0, 0, if it is 0, this will be 0, this will be 1, this is 1, and this is 0. This is the excitation table for T flip-flop. I'll keep it on hand for us. Now we are going to design a mod 6 counter. The number of bits required for mod 6 counter is 3 bits. So we require 3 flip-flops. So 3 flip-flops, so we have to write down another truth table for 3 flip-flops. So what do we have? I'll be having QA, QB, QC as the input. Then at the output, I'll be having QA plus 1, QB plus 1, QC plus 1, and another input is TA, TB, TC. So this is the truth table which we have for mod 6 using T flip-flop. Now T flip-flop, if your present state QA, QB, QC represents the present state. If your present state is 0, 0, 0, next state will be 0, 0, 1. If your present state is 0, 0, 1, the next state will be 0, 1, 0. This will be 0, 1, 1, 1, 0, 0. After 4 here, I have 1, 0, 0, 4. So this will be 5. After 5, it will not go to 6. So after 5, this will be 0, 0, 0. These two states will not be counted. Now what we have to do? We have to see QA and QA plus 1 and write TA. So 0, 0 will be 0. TA, so again 0, 0 will be 0. 0, 0 will be 0. 0, 1 will be a 1. Again, this is 1. 0 will be a 1. Again, this is 1. 0 will be a 1. This I have written according to the excitation table. See, QA and QA represents QN and QN plus 1 in the excitation label, and populate TA, TB and TC. So this will be equal to 0, 0, 0, 1. This is 0. So I have 1 and 1 over here. So this is 0, 1, and the other two will be X. Similarly, if I populate this, this will be 0, 1, 0, 1, 0, 0, and these two are X and X. This will be equal to 1, 1, 1. Everything is a 1. Now this is the excitation table what we have for our counter, mod and counter. Next step what we have to do, that is the first step. Next step, we have to simplify the truth table TA, TB and TC values using K-map. So let us draw 3 variable K-map. So this is a 3 variable K-map. Input we have to consider QA, QB, QC. So whatever we are considering will be for the K-map, the inputs will be QA, QB, QC, and we are going to plot this value. So let us write down these values. So this is 0, 0. This is 0, 1. This is 1 and 1 according to the K-map, and this is 1 and 0. I have 0 over here and I'll be having 1 over here. Now if I plot the K-map, if I write down the values, so here it is QA, and on this axis I'll be having QB and QC. So write down the values. What is the first value? If you can see the K-map and write down the values, it is 0, 0, 0. 0, 0, 0 will be over here. I have a 1 over here. Again, this is a 0, this is a 1, and the remaining two values are x and x. So this is the K map what we have got. Now we have to simplify this K map. First you have to check whether there are octets. There are no octets, no chords, so I have only a pair. So let me select the pairs whatever I am having. So if I see, this will be one pair. I have one pair over here and another pair over here. Now if I write the TA value, TA is equal to, now for this pair, it will be the 0 and 1 is going, so it is QB into QC, QB into QC plus. And for this pair, it is QA. For this pair, we have it is QA into QC. So the K map will be equal to QA into QC plus QB into QC. This is for TA. Similarly, we have to solve for TB. So I'll leave that as an assignment. TB will be equal to, again, if you plot TB values, so I'll just show the K map for TB. Now if I plot TB values, what will be TB values? TB will be equal to, here I'll be having 0, this is 1, this is 1. Again I have a 0 over here, these two are zeros, and here I'll be having two don't cares. And I'll be having one pair over here. If I can solve, I'll get what is TB is equal to. TB is equal to QA bar. TB is equal to QA bar into QC. Next, what is TC? Similarly, if you can solve for TC, so I'll just show how to solve for TC. Everything is 1 in TC. So if I have, I'll be having a 1, and this 1 will form a complete octet. So I'm plotting TC, this values, TC from the truth table. So this is TC, I have TC, I've plotted this. This will form an octet. So TC according to us will be equal to, TC will be equal to 1. So I've got the truth table. Now TA will be equal to QB into QC plus QA into QC. TB is equal to QA bar into QC, and TC is equal to 1. Now we have to design the mod 6 counter. That is using T flip-flop. So I have a T flip-flop over here. T flip-flop, 3-bit it is, 3-bit T flip-flop. Let me write down first, let me write down the outputs. So I'll keep the outputs. This is QA, this is QB, and this is QC. So I have QA, QB, and QC. This one will be QA bar, QB bar, and QC bar. So this, let me write it as QA. So I have QA. So this will be QB. And this is QC, as we know. Now we have to give a clock. So again, clock, I have to give a clock pulse. So actually this is the clock pulse we have to give. Since I'll not be able to see the output clearly, I'll be giving a clock like this. So this clock I'll be giving. We'll make this as 0 and 1 accordingly. But it is a positive edge triggered clock. We can even design it for negative edge triggered clock, but as of now I'm assuming that it is a positive edge triggered clock. So everything is clocked. So this is a clock what we have. So done. Now what we have to do, what is TA? This is A flip-flop. So this one, let me label it as TA. And what is this? This is TB. And what is this? This is TC, T flip-flops we have. Now, what is TA equal to? Anyhow, TC is equal to 1. So I'll give TC 1. So this is my input TC. Where's my input TC? You can see this is my input TC. TC I'm making it as 1. TC is 1. Done. TC is 1. Next, what do I have? Now I have TB. TB is equal to QA bar into QC. AND gate it is. So I take an AND gate. This is an AND gate. So TB is equal to QA bar. This is QA bar. Already we know that. This is according to our logic. It will be QA bar. So this is QA bar into QC. Where do I have QC? I have QC over here. So I can just plot it. You can even simplify the circuit and draw it. So TB is equal to QB into QA bar. So I have QA bar into QC. Now what is TA? TA is equal to QB into QC. TA, Q2 AND gates I require and one OR gate also I require because it is I've just kept it aside so that it is understandable for us. This is TA. So what is TA now? TA is equal to QB into QC. I'll remove this table since it's already done. Okay. So TA is equal to QA into QC. Now where do I have QA? If you can see, this is my QA. And where do I have my QC? I also have my QC. So this is QC. Next, what is the next one? QA into QC I've done. Okay, this is QA into QC is done. Next, it is QB into QC. So this is already QC. I have QC over here. Then I require QB. Just tab the points and you can make the connection, or you can write the values directly like that. So I've connected. Now let us see whether it is working. That's all. This is the simplified connection. Now let us see whether it is working. So I've made the clock 1. This has gone to 0, 0, 1. Next, when I make the clock 1, it is 0, 1, 0. Next, 0, 1, 1. 1, 0, 0. 1, 0, 1. What should be the next state? It should be 0. So perfectly it is 0. Now this is all about designing mod 6 counter using T flip-flop. The next one, I'll take a similar example using SR flip-flop. So design of mod 6 counter using SR flip-flop. So the next one is design of mod 6 counter using SR flip-flop. We have already done design of mod counters using JK, D, T, and now we are doing SR flip-flop. So now again, first let us see the excitation table for SR so that it is easier for us. What is the excitation table? We'll be having Q and Qn plus 1 as the input. and S and R as the output for the excitation table. Okay, so what is the excitation table for SR? This will be 0x, this will be 1 0, this will be 0 1, and this is x 0. So this is the excitation table for SR flip-flop. Keeping this excitation table, we'll design a mod 6 counter. Again, we require 3 flip-flops only. So now let us write the truth table. So what are the inputs I'll be having? QA, QB, QC are the inputs. Then here it is QA plus 1, QB plus 1, QC plus 1, and it is SA, RA, 3 flip-flops. Mod 6 counter requires 3 flip-flops. So SR first flip-flop will be SARA. For the second flip-flop will be SBRB. And for the third flip-flop it will be SC and RC. 3 flip-flops I am using. So I've got this truth table. Now mod 6 it will count from 0 0 0 to, we already know it is up to 1 0 1. So this will be 0 0. After 0 0 1 it will be 0 1 0. After 0 1 0 it will be 0 1 1. After 0 1 1 it will be 1 0 0. After 1 0 0 it will be 1 0 1, and here it will go to 0 0 0. Now we have to populate the table. How we are going to populate the table? See your QA and QA plus 1 and write your S and R values. So if you see the QA and QA, it is 0 0 0 0 means this will be 0x. Next value will be 0 0, so it is again 0x. Next value is again 0 0, so this is 0x. Next value it is 1 0. This will be x0 because I have this is 1 and also this is 1. Next value will be 0 1. Next two values will be x and x. So it will not change because this is x and x. Now go to SB and RB. This is 0 and x. This is 1 and x. This is x and 0. This is 0 and 1. You should keep your excitation table handy, then only you can write this. And this is 0 and x. This is also 0 and x. So it is SB will be 0 1 x 0 0 0 0 and RB is equal to x 0 0 1 x and x. It is 4x. Similarly, you have to write for SC and RC, which I'll leave it as vacant. You can fill it up. I'll write it for SC if you want. 1 0. Here it is 1 0. This is 1. This is 0. These two will be x and fill this column. This is left vacant. You have to fill SC and RC. I filled it partially. So now let us see how the truth table will be written. Now first we have to write the K-map for what? You have to take the inputs QA and QA plus 1. Write down the K-map for SA and RE. Next what we have to do? Next we have to take the inputs QB, QA, QB, QC and write down the, that's what, QB and QB plus 1. Write down for SB and RB. Then SC and RC. So we have to write it like this. So now let us write the truth table. So let us write the K-map since we already have the truth table. Now K-map for SA and RA I'll be writing Again for SB, RB, SC and RC, I'll be leaving it as an exercise for you people. Three variable K-map again it is so I'll be having a three variable K-map. So this is a three variable K-map. Here I'll be having 0, 0, 0, 1, 1, 1 and 1, 0. This is 0 and this is a 1. And what about the axis? The axis will be QA, QB and QC. Since we are following QA, QB, QC. So this axis it is QB and QC. So now first K-map for SA. When I write the K-map for SA, so these two are X and X. Let us put the X values. So these two are X and X. This will also be an X. And write down the values. 0, I'll be having 0. First value is 0 if you can see. 3 zeros and 1, 1. 0, 0, 0 and 1. And the other one will be a 0. Now this is how it is written. Now if you can simplify the K-map, what happens? This is getting simplified. So this will be the simplified term. So what will be SA equal to? SA will be equal to QB into QC. Now similarly, let us solve the K-map for RA. Now what is the K-map for RA? If you can see, RA will be equal to, if I write, so if I plot the X, this will be X, X, 0, X, and this is also an X. Now if I draw it, so this is X, X, 0, X, and this is a 0, and I have a 1. Correct. Now if you can solve this, so if you can solve, this is a pair. So what will be RA equal to? RA is equal to, RA will be equal to QB bar into QC, QB bar into QC. Similarly, we can solve for SB. SB will be equal to QA bar into QC, SB. And what is RB? RB will be equal to QB into QC. This you have to solve using K-map. SC will be equal to QC bar and RC will be equal to QC. So this can be solved using K-map. I have solved for SA and RA and I have shown. Similarly, you have to solve for SB, RB, SC and RC. So now this is done. Now using these equations, let us write down the flip-flop diagram. How many flip-flops I need? I need 3 flip-flops. It is an SR flip-flop. So this is SR, SR and a SR. Yes. So now first what we have to do, we have to write down the clock. So let me write down the clocks. Actually clock, again I'm repeating, it should be a clock pulse. Since I will not be able to show the output correctly, I'm keeping a gate type of gated clock. D flip flop, D lich latch, D flip flop, JK flip flop. Actually, it is given as SR flip flop, but I don't have a clock over here. Anyhow, I will enable it over here. This is the clock. It should be connected to clock. Since clock is not there in the diagram, I'm using this part. Okay, I'm using it, connecting it to enable. Okay, so this we have as a clock. Now what is S and R? Now I've connected a clock. Let us see what is SA and RA. Before that, we can connect our outputs QA, QB and QC. So here I'll be having my output QA. This is my output QB. And I can have the output QC over here. So I have QA, QB and QC as the output. So let me label this. This is QA. This is QB. And this is QC. You can also note that if this is QA, this will be QA bar. This is QB bar and this is QC bar. Okay. I'm not connecting that. Now what is SC? SC is equal to QC. So I have SC is equal to QC and SC is equal to QC bar. That means it should be connected to Q bar. And RC is equal to, so I have RC. RC will be equal to QC. So I'm connecting RC to QC. This is done. Now what is SA? SA is equal to QB into QC. That means I have to use an AND gate. Now SA will be equal to QB into QC. So where's our QB? My QB is over here. Just I'll pull it up so that it is easy for me to make the connection. SA is equal to QB. SA is equal to QB into QC. So QB into QC. I'm just connecting it. This should go to my SA. So I have connected it. It goes to my SA. And what is my SB? SB is equal to QA bar into QC. SB is equal to QA bar into QC. So RA is equal to QB bar. So QB bar is over here. Just I'm taking the inverse since this is QA bar. So this will definitely be QB bar. RA is equal to QB bar into QC. So I have my QC over here. So this circuitry may look a bit complex, but it is easy if understood. So this is what, this is my RA. Next, what is my SB? SB is equal to QA bar into QC. Again, make a connection for SB. So SB is equal to QA bar. So I have QA over here. Let me keep it over here so that. So I'll just keep it over here. Because it is anyhow my my RA. So my SB is equal to QA bar. I have QA bar over here. So since I have QA bar over here, it is QA bar into QC. QC is again over here, just have to tap it. So this is QC, QA bar into QC. So this is what, this is my SB. Next, what do I need? I need RB. RB is equal to QB into QC. So I keep a connection over here. Where is QB? So I have my QB over here. QB, and I have my QC over here. Just tap QC and give it to RB. So this is all regarding connection for design of mod 6 counter using SR flip-flop. Okay. Now this flip-flop should be clocked. I've given it to enable. Actually, it should be a clocked flip-flop. So clock should be connected to each and every flip-flop. There is no clock terminal in the diagram. So I'll not be able to show you the output. Here we should have a clock. So this is a clock. This should be clocked actually. All the flip-flops will be connected to clock. And as and when the clock varies, it will be counting as you have seen in the previous example. So this goes like this. This should be like this. So this is all regarding mod 6 counter. We have seen designing a synchronous counter using various flip-flop SR, D, JK and T flip-flop. Thank you.